All right, section 1.2, part 2, if you will. We're going to continue looking at some patterns today and thinking about things in terms of patterns. And one of the terms that we defined in your last video was this idea of counterexample, and that's where example 3 is going to place us. So example 3 says counterexample, and if you'll remember from last video, the counterexample is something that proves it false. So an example that shows something false. Sometimes there's lots of numbers or values or examples that you can pick. Sometimes there may be only one and it's harder to find. But if it's asking you to find a counterexample, it means you're going to be able to do it. Okay? So here's an example of one where we're asked to find a counterexample. It says n is a natural number. So remember, natural numbers are the numbers kids start counting with. So starting with 1, 2, 3, 4, all right? And it wants to give an example of a number where when you add 5 to it and then divide by 5, you don't get the same thing as when you add 1 to that original number. And this is an example of a counterexample where there are a lot of options that actually work. So can somebody give me a number that they don't think is going to make this work? Just choose a natural number for n and let's check. 3. All right, let's try 3. So what we want to see is if we take 3 plus 5 and divide by 5, do we in fact get 3 plus 1? Well, 3 plus 1 is 4, right? What is 3 plus 5? Yeah, 8 over 5. Does 8 over 5 equal 4? No, it definitely does not. So this is a counterexample. In fact, there's only one number that makes this work. Do you know what number makes this work? Can you tell? 0. Yeah, whoever said that, that's exactly right. 0 makes this work. If I did 0 plus 5, I'd get 5. 5 divided by 5 is 1. And on the right-hand side, 0 plus 1 is 1. 0 is actually the only number that makes this work. However, if I were teaching an algebra class or working with students, sometimes even with numbers, sometimes it doesn't have to be algebra, there's actually numbers written here. This is something that I might expect to see on some student work. What do you think is a student's misconception, if you were speculating, part B, right, that they're making? What do you think they're doing that leads them to believe that, in fact, n plus 5 over 5 is the same as n plus 1? What's that? They might be thinking about 0, probably not in general. It's okay, there's something else that they might be doing. I think so. What canceling do you see that might work or might lead to that misconception?
What if they tried to cancel out the 2 5s?
Yeah, so you see this a lot in student work where people want to cancel stuff and they don't always cancel appropriately. If they try to cancel like this, of course, they're forgetting that the 5 divides the n as well, right? I mean, that's what they're really forgetting. So what they're likely doing, and we don't know for sure, right? They might be testing the number 0. I mean, it's possible, right? But they likely are canceling or reducing or something like that, canceling out the 5s. They might even cancel out the 5s and think they have just n left and not even n plus 1 as a similar misconception. So that's what it looks like they're probably doing. So you're going to see that in this course, as well as the other elementary math, proportional, statistical, and geometry, that your textbook and in class, Dr. Marsh and I are often going to be asking you to examine work and try to figure out what do you think the student was thinking? Because that's what you really have to do when you're teaching, right? It's not always just teaching the method that's right. It's trying to figure out what they did wrong so that you can help them to understand why it doesn't work. And the reason this doesn't work is because the reality is that each of these components is actually divisible by 5, right? That's what it means when we write something combined over the number 5. So the 5 over 5 still becomes the 1, but the 5 in the denominator underneath the n is still there. And that's the misconception that's likely happening on this problem. Does that make sense? Okay. All right, another type of patterning that's kind of fun are called figurate numbers. Figurate numbers are based visually on geometric patterns. So this is not a geometric sequence like we did in the previous, slideshow. Okay, it's not like that. But these numbers are neither arithmetic or geometric, actually, and they can be represented by dots arranged in the shape of certain geometric figures. And you'll also see some other examples in this section when you get to your group work that aren't even dots. They're other images where we're repeating the pattern of an image. And kids work with patterns and images from really young. I mean, pre-K stuff, right? They get the books and it goes red triangle, blue square, what comes next, patterns with images. And you're going to see a little bit more advanced in terms of some triangles and things like that with your patterning in your book. But this is one of the ways of doing figurate numbers, and they have dots. So triangular numbers is an example. So let me get my dots to work for me. So you would start with one dot. Okay, this is image number 1. The next dots look like this. So they're a triangular shape of dots. And then our next series of dots looks like this. And then I'll do one more. So they're not perfect. I realize I don't have great artistic ability, but I think you get the idea. And you could continue this pattern, right? If I asked you to draw the next one, I think you could probably do that, no problem. How would it be different than the one before? What would you have to do to continue this pattern visually?
Add another one onto the base.
Yeah. So there's a lot of ways of thinking about it. You could add another one on the base and then just build up the side of the triangle. I think that's how you just described it. Some people would describe it as adding another row along the bottom, and the row along the bottom would, in essence, become 5 dots that would make everything just larger, right? Yeah, so there would be an addition, one way or another, an additional 5 dots added to this image, right? So what I want to show you is what happens in terms of the numbers of dots that are actually present. So the numerical pattern, actually. So if we're thinking about the numerical pattern, the first dot, there's one dot. How many dots are there in the second image? 3. And then the third image? 6. Oops, I meant to write 6. And then the fourth image? 10. And verbally we described that the next one would actually be 15, right? This is not arithmetic. I don't add the same number to get to the next line. It's not geometric. There's no multiplying by a value to get to the next term. But there is an inherent pattern here, and I'd kind of like to show you what's happening from a different pattern perspective where there's still a pattern. It's just not quite the same from term to term. So notice, what do you get if you go from 1 to 3? Think addition. What do I have to add to get from 1 to 3? 2. What would I have to add to get from 3 to 6? And from 6 to 10? 4. And from 10 to 15? Do you see the pattern?
Yay.
Absolutely. You could repeat that, right? You could keep going with this. You could figure out the number of dots, and you wouldn't have to draw the image if you didn't want to continue with this idea. Now, this idea of going from term to term to term, that's the recursive description that you also heard of last time. Recursive means I need to know where I am and what the pattern is to get to the next value. So this is a recursive pattern. So these are triangular numbers. In particular, you can see why, hopefully, because you see triangles, right? Yeah. All right, so another one is square numbers. Same idea. Should come as no surprise. The first one is 1 dot. There it is. The next one actually looks like this. And then we have one that looks like this. And I'll do one more. Wow, that wasn't good. All right, still definitely not perfect, but I think you have the right idea. They're squares, right? Makes sense that we would call these square numbers. And we can write a numerical pattern that goes along with them as well. So the first one has 1 dot. How many does the second one have? 4. The third one? 9. 16. So without even drawing it, can you tell me what the next one's going to be? It's 25. Now you might have been able to tell me it's 25 based on the fact that you recognize it's going to be a 5 by 5 rectangular square shape, right? Like that's fine. There's actually a really nice way of describing this in terms of a formula. This is n squared, right? They're square numbers, like we think about squaring things. That's friendly. But the reality is that we could do what I just did with triangular numbers as well and see a pattern. So notice here, this is plus 3, and this is plus 5, plus 7, plus 9. Do you see yet another pattern? You do. So there's often, not always, but often more than one way to think about some of these figure-it numbers in terms of what pattern it is to get to the next thing. And this is an example of one. All right, real-world example of something with sequencing and patterns. You guys ready? Like happened in my life. You guys were probably in elementary school, which is really sad at this point. You're making me feel old and you didn't even mean to. In the fall of 2011, the university restructured and we created the Hurley College of Science and Math. And it broke apart some things and shifted some stuff around. And we've done, again, another shift this particular year, which I'm sure you're probably a little bit aware of, maybe. But at the time, we had a dean. Her name was Dr. Blue. And she put this value on the board, 3, and then there was a decimal point, 1415. And she asked us to write the next 2 terms in the sequence of numbers. So what I would like for you to do right now is to write what you would do if I asked the same of you, which I am. I'm asking you the same thing. What are the next 2 numbers, if you're speculating, that come after the 1415? So 3.1415. What comes next? And why do you believe that's to be the case? So write down for you. There's several different things that you could say. So what do you think the next numbers are and why? Okay, so somebody tell me what you speculate might be the next 2 numbers.
I put 1617.
Okay, so this is a very valid guess. 1617, as that would be the next 4 numbers. Okay, did anybody else think that that looked like a reasonable one? You thought maybe that would be it. Okay, cool. Did anybody else put anything different than that? Okay, so let me tell you what everyone in the room put. Nobody in the room that day put this down. So I'll erase your last 2 because I just asked for 2 so we compare. Everybody in that room wrote 92. It's pi. I mean, that would be the next 2 digits of pi. So what our dean was wanting us to recognize, and in fact, we kind of did what you guys did. Well, we looked at it and we said, well, duh, it's obviously, and we used where we were coming from our prior knowledge, our prior experiences, and as scientists and mathematicians, it's pi. I see 3.1415, and I think we're talking pi. And you see 3.1415, and especially given the lesson we just talked about, right? You're looking for a pattern within the numbers themselves, and you saw 141516. So what I talk about when I bring this up, because this is the same thing that she talked about at the time, is the fact that there's not always one intuitively right answer. So what we used that day in that room, and what you used right now when you did this, is you used what's called inductive reasoning. You took a pattern and you speculated what would happen next. And it's speculation. Inductive reasoning may not always yield exactly the same answer from person to person or from groups of people to groups of people. And so it can be very misleading sometimes when you take something and try to generalize it when you're not sure the construct in which you're generalizing. So it's interesting, right? Yeah. All right, so this is actually it for 1.2. So we're going to stop now and we're going to do some group work.